Hello, welcome everyone. It is a pleasure for me to introduce Professor Javier de Lucas from the University of Warsaw. He will be our speaker tonight and will introduce us to the world of infinite dimensional jet bundles and some applications of it. So, Javi, whenever you want.
Yeah, thank you. For me, hearing for you that I'm a professor is a little bit weird. I must confess. Okay, so the topic today is about infinite dimensional jet bundles, and I will do it dimensional jet bundles, and I will try to explain the most important things about this theory. And I will introduce some related notions that are very interesting. And I will give you also some topics that have not been developed but could be developed. Okay. These theories related with the so-called diffeties. Yeah, diffeties. Diffeties. And the so-called secondary calculus. Truly speaking, these ideas were developed mainly by Vinogradov. We had Vinogradov several times in Warsaw. I could see him to explain some of his ideas, and I also see how Polish people try to. Oh, they have the conversations, tough conversations with him. And it's, as much as I remember, he finished shouting each other several times. Okay, so let us say this is a world theory. Okay, you for sure know how jet bundles work, finite dimensional jet bundles, and infinite dimensional jet bundles is, well, as you can imagine, is an infinite dimensional manifold. So somehow you have to develop some theory to deal with them, and this theory is about infinite dimensional manifolds. But in this case, there is an approach that makes things easier. Indeed, you will see something interesting is that when you deal with jet bundles where contact structures, K contact structures appear, there are several structures that are difficult, let us say. And the fun thing is that when you use infinite dimensional jet bundles, things that are more difficult in finite dimensional jet bundles, they become easier. Okay. The thing is that the first approach, when you start thinking about infinite dimensional manifolds and things like that, you start thinking about, come on, that this is difficult. This is not a standard manifold, finite dimensional. Many things will not work. Okay, so the theory is hard, but the thing is that once you manage to prove certain things, it turns out that the theory allows you to do much more things than usual, and things are easier in practice. So it's kind of interesting that a theory that theoretically seems to be hard, at the very end when you apply it, it's softer and it's easier than previous things. So this will be a introductory talk. So I will give the main notions, and I will assume that you know something about finite dimensional jet bundles. Okay, so the initial structure is that you start with a 13 bundle. Yeah, it's locally trivialized as always, and you can think for simplicity that you have just a 13 trivial bundle of this way. Okay. So in here you have the space of sections. Sections, as you will know, you know for sure, there are maps from the base manifold to A in such a way that the projection of the sigma, which map and P is the identity of the manifold. We write E, or we also denote it by E, or sometimes we denote it by P, depending on how it's easier for us. This is called the space of sections. Space of sections of P. We assume that they are, they are smooth, and I will assume that everything is very easy in the sense that this bundle is trivial. Okay, let me write in here that it will be some K will be easier. Okay, some something general. So when you start thinking like that, in this space of sections, you can introduce a certain equivalence relation. Okay, and how you do it? When you have a certain section, it's indeed in this scheme something that it goes in this way. Okay, and so I suppose that the bundle is trivial. So for a certain point of in you can say that the image is just X, okay, because the base manifold is a section, it should be the same. And then you will have some function of the point where F is something from M to R. Okay, so once you have such a thing, you can introduce a certain equivalent relation. That this is what usually is done for K manifolds, okay, K-jet bundles. And these relations say that you have two sections, okay, of our bundle. Let us say two. Okay, one of these equivalence relations is of the sort depending on a 1 point on M, yeah, third time index. Let's say M. Okay, and what does it mean? Mean, yes, that the value of sigma 1, sigma 2, and X is the same, and the partial derivative, all the partial derivatives of X depending on third time variables. I mean, this is a multi-index, okay? X, let's say that F1 partial F2 X, X where, this is just a multi-index, okay? It's just A1, A R, let's say that what R is the dimension, the manifold, and these things are just integers, okay? And the thing is that you define the absolute value of the multi-index, the sum of this alpha 1, 2, R, okay? So this relation means, and in short, is by saying that this thing, that the Taylor expansion of the two sections is the same up to order K, okay? So the thing is that this relation is geometrical. It doesn't matter that you use some coordinates or not. Okay, when the bundle is not trivial, it works. Okay, when you pick up locally a local actualization, then you fix some third time way of identifying the total bundle in this way. What you think is that this also works. If it works for third time coordinates on the base manifold and the total manifold, it works for everything. And the equivalence class of these things are the so-called, well, this is up to L, sorry. This is what is called these classes. Okay, Xn build up the set of equivalent classes, and this is written like J and X, okay? It's the space of equivalent classes related to this equivalence relation. And if you pick up all these structures, you will obtain that n-dimensional jet manifold. That is just all these relations, equivalence classes, okay, for different values of X, but always up to order M. Essentially, that means that you have sections, okay, and this is the all the possible Taylor expansion of these sections up to order N. Okay, essentially this is space. This space has certain natural coordinates. Normally, if you pick up coordinates on M, that is, let us say, X alpha, and if you write locally trivialize, if this is the case, or K, okay, so the coordinates in here can be written like yi. So when you go to this space, in this space, the coordinates will be this, and the derivatives of higher order of the coordinates y are I alpha. Okay, this is natural coordinates, adapted coordinates, natural coordinates. Okay, and of course, it happens that these coordinates, the indexes that you will have in here, indeed, you will have J, because this will be as always the possible derivatives of the variable y in terms of x alpha. Okay, so you have a 37 natural coordinates. If by means of this, you can say that these things in a manifold. Okay, maybe you know this. Okay, so what is the point now? The point now is that when you're dealing with this, you're starting with a certain differential equation up to order n. Okay, and the thing is that this theory about jet bundles is just a geometrical description of differential equations. It's just a manner to describe the space where differential equations, partial differential equations live, and ordinary differential equations in a particular case. But there is a big problem about that. And the big problem about that is that when you work with differential equations, partial differential equations, sometimes you want to obtain certain constants of motion, or you want to prove certain things, and you have to make additional partial derivatives of your solutions. But the problem is that geometrically, if you have an n-order differential equation, geometrically, everything must live on a jet bundle up to order n, because only can deal geometrically with coordinates with corresponding to derivatives up to this order. But if you want, for some reason, to perform a certain additional derivative and to obtain something that is of order n plus 1, everything fails. That means that your geometry doesn't work, and you have to start with another higher order jet bundle, describe everything on this manifold, and repeat all this stuff. But this is annoying, because sometimes you even want in theory to make many partial derivatives of equations and describe them geometrically. But an n-jet bundle just allows you to deal with partial derivatives of order n. And sometimes, many times, you want to deal with partial derivatives of higher order. So that's why you will define the infinite dimensional jet manifold. And how we can do it, okay? So take into account that when you have this J0E, that means that in this relation here, the order of J is 0. I mean that there is no derivative, because a derivative order 0 is no. So this is exactly E. And then you have J1, okay, where you have certain coordinates that go to up to order 1. So you have a natural projection in this way. You also can go to J2. You can make a natural projection onto first order 0, and you can go and go and go and go for E, and so on and so on. So, okay. And if you do so all the time, you can configure a certain J infinite that contains all the possible variables. Okay. And eventually, well, obviously, you see that the variables of this manifold are these, the x alpha, the y alpha, and all the derivatives, all the possible variables corresponding to all the derivatives of the Taylor expansion of sections from M to E. So this guy, normally, apart for trivial cases when the base manifold is 0, has dimension 0, this is an infinite dimensional manifold. And this is a hard one to deal with. Well, hard one, theoretically. You will see in a while that it is easier to do. So, when you have this scheme, okay, this is normally called the inverse limit. It can be described by means of a categorical approach. I will skip that. This is something probably Adam knows, at least. And the thing is, you want to describe these things. To deal with differential geometry, one of the main things you have in the differential geometry are functions defined on a manifold. So you know that you will have functions always. Well, here you can even, you can have this space on function, you can have this space function, you can have this space of functions, okay, and so on, so on, and so on. And the thing is, this thing is special, and I will tell you how to define it, okay? So naturally, you see that since you have a projection from the J1E to E, you can pull back any function on E with respect to this projection. Sometimes it's written P1, this is sometimes written P2, this is written P3, and this is, P3 to 2, P4 to 3, and so on. So the thing is that when you have these things, each function on every such a manifold can be considered as another function on the upper manifold. Indeed, when you pull back, for example, certain derivative up to order 0 in here, you will get, doing the pullback, exactly the adapted system with the coordinate defined naturally on the J1. And you can repeat this for all of this stuff. So its function, space of functions on E can be naturally embedded into the following one, into the following one, into the following one, and so on. And this is an inverse limit of these things. And this is written in the following way. It's from 0 to infinite of all these things. But, and this is the important thing, okay? Sorry, this will be this stuff. And this is the first thing you have to think of when you are dealing with this. This space of functions is a space of functions that is given by the sum of these spaces. H1 of int can be included into the space on function, the total space on a bigger jet manifold, but every element of these spaces, every function in here depends only on a finite number of variables. Okay? These variables can be variables up to order whatever, okay, any order. But every function in here, if you have a function in this space, it means that this is a function that can only depend on one of these spaces. And if it belongs to one of these spaces, okay, it means that it must depend on just a finite set of variables. So if you have that f belongs to this thing, this is equivalent to saying that this f is a certain function of certain variables, x, alpha, y, where y must be lower or equal to a certain constant Q1. For example, it's not allowed, if you write, for example, f, and you have the variable t, you have x, you have the first derivative, second derivative, and you see that the function depends on all derivatives. For example, this, where this is, well, let us write it, it's a little bit cumbersome, but I expect that you will understand it, okay? This thing does not belong to this space. You see, it's something that depends on all the derivatives. So it does not work. So the thing is, when you have this manifold, okay, as infinite dimensional, indeed, it is called something called preset manifold. I will not go into details because it's very hard, but the thing is, this space that it is here defined on J alpha is, as I said, there are functions that can depend on any set of coordinates, but yes, a finite set, okay? So this is very useful in applications because when you have, as I told you at the beginning, you start with a partial differential equation of order n, and you want to make some partial derivative of it and to deal with, make some expressions or do whatever. So no matter how many times you will derive it, it keeps on being given a function that it belongs to this, okay? So this is the first thing you have to think in here, okay? The other thing I want to tell you is that when you have a third plane J and F, okay, this manifold had some structures that were very interesting. Sorry, and this structure are so-called, well, it's the Cartan distribution of certain and stuff like that. So imagine again that you have these coordinates, and this thing, okay, natural coordinates of this jet manifold up to order n. So you see, you know, this would be, the order of this would be lower or equal to n. So you have something called the Cartan distribution. The Cartan distribution is just a third time set of derivatives, okay, to say this way, and you will see something fun. is just this, okay? And here, what you will have is the partial derivative of y(e), and here you will have this, okay? In terms of the coordinate a, and you will have many things. Wait a second. Yeah, you will here add, for example, all possible j's, all these variables, okay? And here you will get that this variable will be derivated again with respect to this thing, okay? And this up to a certain order, okay? This is this up to order n, and this will be, these things will be up to j that will be lesser than n. Why? Because when you will have some of these elements with a joint print of this manner, okay, the thing is here you will have these derivatives of the coordinate plus alpha. So to ensure that this thing exists of this manifold, is a variable that has derivatives up to order n, you have to ensure that the set of derivatives you perform on this variable must be lesser than n, because when you add here, you have to have this. And then when you have this expression, you have these total derivatives with respect to the following one, but these are, let us say this, where this thing has order n. And this is the Cartan distribution. They are derivatives of this kind. Okay, I will give you some particular very trivial case. In mechanics, you can have this manifold. Imagine that you have k times r, okay? And here, what you have is, for example, j1 of this thing. This is going to be p, and this is going to be it will be this case. So in this case, when you write the Cartan distribution, you pick up the variables on the base manifold. Here is partial t, and then you write the variables in here, y, e, and then here you have to write the derivative of this variable in terms of t, so it will be this, something of this sort. Okay, and you see, since this is up to order 1, here is 1 order less than that, and here you will have these derivatives of higher order. So this thing, this distribution is interesting, and it's not involutive. Indeed, if you make this Lie bracket, you will obtain, by doing the corresponding calculations, this vector field, but this vector field doesn't belong to this structure. So it means that C is not involutive. Okay. Indeed, in certain cases, okay, it can be shown that this is a so-called contact structure. In another more general cases, this is called a K-contact structure. In all these cases, the distribution is not involutive. Okay. One thing you have to take into account is that you can take a look at this. And this is quite interesting because it's like when you have a 13 function, it's like making the total derivative. You know, because when you have a 13 function that depends on ti and you perform the total derivatives of terms of time, what does it mean? It means that you have to make the partial derivative of terms of time, and then you have to make the partial derivative in terms of time of y, and then the total derivative of y in terms of t, that is d. But you know, this is in this thing. So these partial derivatives that you have in here, they are just a geometric manner of saying that you are making total derivatives of functions, okay, up to the first order. Higher order, you will not be to deal with it. So this is the thing. The thing is that when you have the infinite dimensional E, whatever it is, it turns out that when you repeat this, for example, in the previous case, what you will get is this. Y, this is the first, this will be the second, okay, you will continue with the third, the first derivative, second derivative, and you go and you say, and which is the highest order? Well, here there is no highest order. This total derivative goes and goes and goes and goes all the time. Okay? So this is the fun thing of this, because it turns out that in this case, what it happens is that this distribution you have in here, it does not end, and you don't have these terms in here, but you have just one vector field. So it turns out that this Cartan distribution is expanded by one element and is involutive. This is the Cartan distribution, the total Cartan distribution, and it turns out that it is involutive. So when you start doing this Cartan contact distribution, K contact, and this up to order n with jet bundle, it turns out the distribution is not involutive, and there are lots of problems related to the fact that it's not involutive. But when you go to the infinite dimensional jet manifold, that you say, well, come on, it's infinite dimensional, it must be very difficult, it would be a nightmare. It turns out that it's just an involutive distribution that can be integrated normally. So it becomes easier. This is what happens with this infinite dimensional jet manifold, that at first sight can be a little bit frightening, because when you see them, you think that they're gonna be very hard. But when you start dealing with them in practice, it turns out that it solves many problems. Theory is harder, of course, in certain cases, but in practice, it turns out that it is easier. So the other thing you can see is that here, this is the Cartan distribution is dimension one, because the base manifold is R. If you had some n manifold with dimension p, you could have just p vector fields. So the Cartan distribution has the dimension of the manifold. So the dimension of this thing is just the dimension of in general of the base manifolds. If you have E onto E, where here you write RK times M, okay, and you do the J infinite over L, it turns out that here this space is endowed with a third times C infinite distribution that it is involutive. Okay, and this involutive distribution, as I said, is the infinite dimensional Cartan distribution, and it's involutive. But if you do just up to order n, it turns out that it does not work. I mean, that is not involutive. You will have K contact structure, you have contact structures and things of the sort, but it will not be, in this case, in the infinite dimensional case, it turns out that it is easier. And the other thing is that the dimension of the Cartan infinite dimensional Cartan distribution is always the dimension of the base manifold of your bundle. So it's very easy. Okay. In case of the n jet manifold, the dimension of the Cartan distribution, it's harder to obtain. You remember, you have to work out the number of partial derivatives of the coordinates of the fiber in terms of the coordinates of the base, and sum all these possible derivatives from order 0 to the higher order. So it's a number that you can calculate, but it takes some time to obtain. It depends on these variables, and well, here it's pretty much easier. So the thing is that when you have this C infinite, this is involutive, and you have to be careful, because infinite is not finite dimensional manifold. So the hard part is that since it's not finite dimensional manifold, Frobenius theorem does not work. Okay, for example, you have a vector field on J infinite, and it may happen that it has no integral cubes. Okay, because in infinite dimensional manifolds, general ones, okay, you don't know if a vector field has integral cubes. Okay, you also have to think one important thing is that vector fields of these infinite dimensional manifolds, they are derivations of the space of functions, okay, as always, okay, certain derivations of the space of functions. And you have to take into account that these derivations act on functions of the manifold. And these functions of the manifold, you have to remember that they may depend on any large number of coordinates, but the number of coordinates is always fixed. But vector fields can depend on any number of coordinates. They can be infinite. And why? Even if a vector field depends on an infinite number of coordinates, like in this case, okay, this thing, when you apply it to something that depends only on a finite number, you will always obtain a function which depends on a finite number. So this is fun, okay? This is the main thing from a practical point of view. On infinite dimensional jet manifold, functions depend on any number of coordinates, but up to a finite number of them. But vector fields can depend on any number, okay? You don't have any problem. And with differential functions, okay, and one forms, it's the other way around. It turns out that since they will be differential of 13 functions, okay, for example, or they will be linear combinations, they must depend on a finite number, okay? If you have a finite number of differentials of these natural coordinates, and you apply to a vector field, okay, the vector field can be an infinite number of partial derivatives, but since the differential for they will have just a finite number of coordinates, you will be always able to make the contraction and things like that. So it's a play, okay? So functions, any big number of coordinates, but finite. Vector fields, whatever, okay? I mean, the number of these things. This function in here that must depend on a finite number. Differential, they have just a finite number of differential of the coordinates. So this is the thing. Anyhow, okay, the thing is, you are interested in looking for third-time integral sections of this distribution, of this Cartan distribution. What is an integral section? As always, you pick up a section, you pick up the tangent bundle to its tangent space, and the value of the tangent space to these sections must be this. Okay, so imagine that you have, for example, an R2, here you have an R2 times R2, whatever, okay? You have the standard projection, and imagine that you have the J1 on this E here. This is normally called P1, P0. This is called P. This is called normally J1P, okay, in this case. So sections in here, okay, well, let me write to where it would be easier. So you have a plane, and here you have R3, and sections are mapping from here to here. They're to R3, they will be just surfaces, okay? And to classify the surfaces at this point, you have the value when you have here sigma x, this value, and you will have the partials of the function. Remember that sigma, this will be x, some function of x. So the first order jet of this section at the point x is just this thing. So it's just x1, yeah, at point x. And the other thing, it will be x2 at point x. So this value, this value, this value along to x, they fix the equivalent class of this section. This is, sometimes it's called sigma x1 because it's at point x or up to order 1, or sometimes it's written this way. Both options are okay. Okay. So this is the one of the elements of the J1. And when you have this section, you can define the so-called lift. Okay, this is a section, and when you have this thing, okay, you can make this. You can do this thing, the lift of the section to the first jet bundle at the point x. And what is this? Well, the first value of x, the value f of x. And the following thing are the partial derivatives. No, I will write just f, okay, because it would be easier. X, this is just the lift to first order. And you can do the lift of this of second order, and anyone knows how it's going to be, yeah? It will be the same as before, then this thing, then this thing, 1, 2, 2, at x and 2, 1, 1, x, and so on, so on. And so when you have a third section, that is something that goes from the base manifold to E, the J1 is something that goes from here to here, and you can do the projections, the 2, and so on. And you can define also the infinite dimensional lift. That is something that goes in here. Okay, these are called the lifts of the infinite dimensional lift. Okay, so when you have a certain section and you up to all the infinite jet bundle, you have this infinite dimensional lift, and you wonder how this works. Yeah, and when you have something of this sort, okay, you can stay wonder which is the tangent map to this thing. Okay, tangent map. Okay, it's something that goes from Dm to the tangent space to this, and then the normal way. Yeah. So you can understand that when you have this, n has coordinates x alpha. So to obtain the tangent space, you will work this, yeah, in here. So when you obtain this section, okay, you have to take into account that sigma of x is something like x f of x, the first derivative of in terms of x, okay. The second derivative is I will write this way to say that the second derivative kind of like this, and so on, so on, so on. So look what is going to happen. The thing is, the tangent to this infinite, well, one or infinite, sorry, it will be the partial of this in terms of x times this. So you will have this thing, the first element. Then you will have to make the partial of the coordinates of f in terms of x alpha, yeah, times the corresponding coordinates. So what you will obtain will be, let us do this thing, yeah. And the following thing you will obtain is just this thing, second x alpha, x beta, and so on, in alpha, and things like that. But the important thing I want you to show is that this thing, what you have in here, is just one of these vector fields of the Cartan distribution. These things, they are called the total derivative vectors. And this thing you have in here is nothing but the total derivative vector field, alpha, in the prolongation. So you see, the fun thing is that when you work out the tangent map to these partial derivatives, you will get one of the vector fields that belong to the infinite dimensional Cartan distribution. And you will notice that this has dimension in M, yeah. So the image, according to this, will be the dimension of this all, the alpha. Indeed, the tangent space to the image will be spanned by the Cartan distribution. I mean, what you are saying is this. Is the Cartan distribution in the image of this. So this is the fun thing, is that when you have a 13th section, it turns out that the tangent to the leaf of one section is the Cartan distribution, the infinite dimensional Cartan distribution on the infinite dimensional projection. So
sorry,
that tells you
may I ask you something?
Yeah.
So in other words, they are just vector fields that are horizontal on the bundle of J infinity E.
Yep.
Okay, so in other words, we can, instead of Cartan distribution, we can work with the Cartan connection, right?
You can say that way, yeah. You are making a connection with it.
Okay, yeah, exactly. Thank you.
Yeah, welcome. You can consider vertical vector fields. You can consider some horizontal inspired by the Cartan distribution, and you will get a natural connection.
Yeah,
and something
exactly,
that lives in here. Yeah,
exactly.
And this connection is natural for jet bundles, and it gives rise to many structures afterwards. So it's a good thing. The important thing also is that when you have this Cartan distribution, you are very interested on the integral submanifold, because this integral submanifold, it can be proved that they are only of this type. Okay, when you have certain integral submanifold with Cartan distribution, you will notice that this is the lift, okay, of something that comes from a section. So if you have a section and you pick up the lift to the infinite dimensional case, since this is a section, you know that it's a mapping from the dimensional manifold to the space of section. And when you expand the total, no matter how many you do it, okay, every point can be parameterized by elements of the base manifold. So it is always some submanifold of the same dimensions as the basis. And they are always the integral submanifolds of the Cartan distribution. So this Cartan infinite dimensional Cartan distribution is very nice, it's involutive, and the integral sections, they're very important because they will be the least of certain sections. That is what you wanted to do. Oh, you see that this at the very beginning it seems to be difficult, it seems to be quite a mess, but when you start thinking of it, it's pretty much easier. Okay, it's very natural. And it's it's like comparing integral distribution with contact distributions. They're much easier, okay? There are 13 aspects about the fact that they are total dimensional, but they're easier. And there are many things about prolongation of vector fields and the geometric approach to partial differential equations. With this stuff, it's much easier. Okay, you will not think it will be easier to deal with it. So I see that, well, as you can see, this is a difficult topic, but I expect that the things I will tell you, they will be good for you. And I will not go much into details of application because I have the time. But I guess that it would be enough to say something of this. It's an invitation to say it that way. So let us say this is the usual stuff, okay? You have a certain jet bundle. You have a 13 bundle, you can obtain that K jet bundles, you can extend to infinite dimensional one, like a inverse limit. And when you have this, the functions on it, they are functions depending on all the coordinates up to a finite number of them. When you have vector field, the derivation of this space of functions, the partial can be an infinite number. The coefficients, they are functions that might be dependent on a finite number. The differential forms, the differential of the coordinates, you will have any big number, large number, but they must be fitted and things like that. And the Cartan infinite dimensional Cartan distribution is involutive. The integral sections of the Cartan infinite dimensional Cartan distribution, they are the leaves of sections of the initial one, definite leaves. Okay, and now the thing that I will tell you is that how to deal with PDEs. And PDEs and infinite dimensional jet bundles. Okay, so for PDEs, the natural stuff is that what is done normally in differential equations, for example, when you have this, for example, this equation, you let us say this will be, let's see, square U. This, for example, one of these equations, this is normally defined in the following way. You have R2 because you have two variables, independent variables, the X, you have one parameter U, so you define some total manifold of this type, okay, where U depends on it is the variable on the fiber. And to describe this thing, you need here to here. Okay, here you have T, E, Q, and you will have this thing, you will have this thing, and you have this thing, this thing, and this thing. And okay, these are the variables in here. So normally when you have such a partial differential equation, what we do in geometry is consider that you have a 13 functions. You can consider that this is a function that depends of t, x, and all the possible derivatives of u with the index of the multi-index bigger or lower to 2. So this is a 13 function, and when equals to 0, this gives us solution. So what you have is a 13 submanifold. This differential equation is a submanifold. Which one? The level sets of a 13 function, this function. So normally in differential geometry, a partial differential equation is a submanifold of a 13 J and E. This is the normal stuff of thinking of partial differential equations in geometry. A partial differential equation is just a submanifold. And solutions, what are solutions? Solutions, when you have a 13 solution here, this U is something that is a 13 function Tx, but you can write it like a section. You can think of it like something that gives you Tx, yeah, and a 13 function of Tx. So this is a section of, you know, R or E to R2. This is R2 times R. And when you have 30 solution of these, okay, what you are saying is that the prolongation of this section up to order 2, they belong to epsilon, okay? You can say that this is included here, okay? So you say that a PDE is a submanifold epsilon of U2 and E, okay? A solution to epsilon, this is by definition is a section of the manifold to E such that the, well, if you we write that this is including J and E, no, okay? This is a section such that the prolongation up to order n belongs to this submanifold. So when you are solving a PDE, what you are looking for is for the prolongations to the jet manifold, the corresponding jet manifold of a section. Okay, they must be included. What is the point of this? That many things like symmetries, conditional symmetries, or other properties that are described in partial differential equations can be described geometrically quite nice. People dealing with partial differential equations, many of them, they love coordinates. Geometrically, it's easier. Well, it's easier. When you try to describe general properties of partial differential equations or general methods, it's easier to do it in this geometrical manner than in coordinates. Normally in coordinates, it's cumbersome, it's complicated, but you know, for a particular example, you have to do it normally in coordinates. But in other cases, it's not like that. Okay, so it's something that it's interesting. So the thing is, this is the usual stuff. The only problem is that when you have solution for a PDE, for example, in this case, for the differential equation describing the sound waves and things like that, the problem is that sometimes you want to work out, for example, higher derivatives of the solutions or whatever. Why? Because sometimes when you have a PDE, okay, and it's complicated, by making partial derivatives of the solutions, you can find that there are solutions of a higher order, simpler partial differential equation, things like that. There are many methods devoted to that, or you can find certain constant of motions, integrals, or whatever. I do this stuff. What's the problem? That making this thing makes you to have to deal with different orders, partial derivatives of different orders. And sometimes the order, it can be quite large. So the thing is that with this, the usual stuff by Olber is the guy who deals with these partial differential equations most. I'm one of the best in the world. But there are many other people dealing with this. Okay? And the problem is that in practice, geometrically, you need something that allows you to deal with an infinite number of partial of coordinates or the derivatives of higher order, whatever. So in that case, you have to deal with this infinite dimensional stuff and then J infinite. How you deal with it? What you do is just to consider this object, okay? The infinite prolongation of a certain manifold. So let us do this for a certain example, okay? Example, imagine that you have the equation you had before. And you know that this is equal to 0. This is just one function, yeah? That is one. So if this is equal to 0, that means that if you apply the total differential, you can consider like it's a function in the infinite dimensional jet manifold, and you can start applying the total derivative of this function. And if you do with t, you will obtain the third derivative in terms of time. This is like making the partial derivative, the total derivative in terms of time. So it will be c squared phi u t x squared equal to 0. You see, this is something like lives in J free E. That is something that it can be understood also as a function on J infinite. So if this is satisfied, okay, the higher derivative of the function, the partial of U in terms of time must satisfy this, okay? So if you have a certain section that is solution of this, okay, you have a certain solution, okay, that means that this must belong to this, okay? What tells you this thing is that this J free, okay, not only belongs to this, because the first, second derivatives, they will belong to this, but they will also, okay, belong to the set of zeros of this thing, okay? So you can write that this is a function of this. But not only, you could do, for example, the dxf and to say 0, and they will belong to this also. They will be zeros of this, of this, of this. And the fun thing is that when you get higher and higher and higher, you can make more and more of these things. So if you have that, you have an epsilon, and this is the 0 of third time function, okay? Doing this, okay, is just making the submanifold given by the zeros of all the total derivatives of any order of this function f, doing equal to 0. So if you have that, you have a third time submanifold, normally is defined the partial derivatives of the 0 of a certain function. The infinite prolongations is just to consider how they will have all the partial derivatives of your solution. So the fun thing is that the dimension does not change. Okay, I mean, if this has dimension, for example, I don't know, 1, 2, 3, when you get higher and higher, the number of variables when the jet manifold grows, okay, they are somehow related by the fact that you have more conditions. So it turns out that your manifold will not change, and it's always the same. And it turns out that the solutions you want to obtain, do you remember, they are the integral sections of the Cartan distribution. So this is one thing fun. I could give a course in this about this. It's quite interesting. And the thing is, when you have a certain thing of this sort, the thing is that you can prove that the Cartan distribution is tangent to it. Okay, it can be proved. This is a theorem. Cartan distribution C infinitive is tangent. It's tangent to epsilon. You can see that this is real because when you have a certain function that define this thing, they are the total derivatives of this. So if you apply the total derivatives that they expand the dimensional Cartan distribution, the differential of this function f, okay, must be zero, because this is the way of defining this infinite dimensional prolongation. So what you are doing is that saying that the Cartan distribution, infinite the Cartan distribution must be tangent to this. And this pair, this with the Cartan distribution is called a diffuity. Okay. The infinite dimensional prolongation of a Federated manifold, along with the restriction of the Cartan distribution, the infinite dimensional Cartan distribution to it, which is tangent, is a pair that is called a diffuity. And this is the main thing that appears in the second calculus, this theory. And let me tell you that this is what I have told you, just the easiest thing. Let me tell you that this is just some soft introduction to the topic. One day I can prepare this with more time and make more, give more details and things of the sort. But the main object is this. It's just the Cartan infinite dimensional Cartan distribution, which is integrable, okay, and the infinite prolongation of a Federated manifold. Okay, and these both things is called a diffuity. And the thing is that there are different things in geometry and differential equations, and it's quite fun, but they are not described geometrically. For example, maybe you remember that sometimes certain difficult equations, like let's say, let me think of it, okay? For example, it can be this thing, okay? This thing is a first order differential equation, okay? Depending on one variable, so it's something of this sort. R, okay? This is the time. This is R squared, it would be X time. This is a first order differential equation, so it lives in your 1p or E as you wish. Okay. So the variables in here will be X, T, E, the X, the T. Okay. And this is a set of variables, and this is certain submanifold. The submanifold is given by X time minus 1, X, T plus X, 1, 0. This is just your submanifold. Okay, in here. And do you remember that in this case, T is considered the time, the independent variable, while X is considered to be the dependent one. But then you did something in the first year and you say, we can do it the other way around, yeah? And then it turns out that you have this equation that is linear. Yeah. But here there is something different, because what you are telling us is that X is dependent, X is independent, T is dependent. So you are changing, you are giving a second projection instead of T doing on X. Okay. And somehow you are making another first order P2. Let's just call this P1. Okay. And these two are diffeomorphic. And this epsilon that lives in here, there's some way of relating both things. This transformation from one to here and another stuff. And this is easier. This way of changing the base manifold is called orthographic transformation, graphic transformation. Okay, and this is the fun thing, no geometric description. So far, no one has described this geometrically. Okay, so I mean, something that that is done in many cases in partial theory of differential equations, that it is changing the roles of dependent and independent variables. It destroys absolutely everything. It destroys absolutely the jet structure. The fun thing is that it does map one bundle when you prolong it to infinite dimensional stuff. There is a one-to-one relationship with differential one of the one bundle and the second bundle. So this is a so-called transformation of diffeomorphisms, and this works. And you could describe these holographic transformations by means of diffeomorphisms, and no theory of it is done. So what I gave you is just as much as I could check several years ago, something that is not done. You can sit down, write it down, write a paper, and it could be accepted. Probably, because I said it's something that people working on partial differential equations do frequently. Yeah, it's something like on first year of your study you did, yeah, on second, and you did many times, and it's absolutely different because it destroys everything we know about jet bundles, because you change the projection to relate one to the other is different. But nevertheless, if you go to the infinite dimensional one, the integral sections of what you think, it will be the integral sections. I mean, the infinite dimensional prolongations. And they will be the same at the beginning and at the very end. So no matter if you start by the first difficulty structure related to this differential equation to the second, there is a one-to-one relationship between them. Then this is called amorphism of difficulties. So holographic transformation is a certain particular kind of morphism of difficulties. As I say, as much as I could check, if you write this in a paper in a couple of pages and you make the details, some of them they are not true, but can be done. It's a paper, so have fun. And I think that maybe we can finish.
Thank you very much, Javi, for your talk. Very interesting. Are there any questions or comments?
It's been weird.
Yeah, looks like this wasn't the easiest one to follow.
Yeah, sorry, just to make sure, I mean, holographic transformation is very well known, right? I mean, people do it in coordinates.
Yep, but you know, geometrically, no.
Okay, geometrical, okay.
I mean, it's done in many cases for many partial differential equations. There are many results,
exactly.
But geometrically, the point is absolutely different from what you did. Yeah, yet manifold. The thing is that when you change the role of the dependent and independent variables, there is a very hard relation between both things, between both manifolds. There is no natural way to go from one jet manifold to another. They have absolutely. I mean, when you change the nature of the dependent and independent, the first order, the second order, the third order jet bundles, they don't have the same dimensions. They change absolutely. So there is no natural way to make a transformation from one to another. But if you go to infinite dimensional, the thing is that the distribution is integrable, and there is another relation in some cases. Yeah, in this case is this case is easier, the easiest one. If you try to do it for pure theories, it will be found. But as you said, it's done every day. Yeah, seems to it's like not in a stupid way, like number theory. Yeah, the idea is very easy, but to prove anything is very hard. Try it by yourself, and you will get quite easily convinced.
Okay, thank you.
Yeah, work.
More questions or comments? No. Well,
today nothing. Okay.
Okay.
Anyhow,
so
thank you.
Thank you all for attending. Next week we are.
I have a question. Yeah.
Go
Is there any like correspondence to infinite dimensional jet bundles of Frobenius theorem? I mean, is there any approach to?
Okay. No. There's. I mean, anything you can think of doesn't work.
Okay. But you in this case you can talk about involutivity, right? Yeah,
you can talk about evolutivity. The problem is that evolutivity does not meet integrability.
Yeah, sure. Okay.
In general, as I said, the easiest case is that they are just vector field, yeah? And there are many cases where you have just a single vector field, okay? And integral Qs, they are the integral sections of the distribution of the vector field. And it doesn't work. You will not have flow, you have integral Qs in many cases. You're fucked.
Okay. Because I guess that in infinitesimal symmetry that you will talk someday are somehow the vector fields that are in involutive correspondence with C, right?
There are 30 cases with additional conditions that the answer is yes, you can do it. Indeed, there are cases, for example, you have a certain Lie group action, a certain jet manifold, you can extend this mapping to all the higher order, and the vector fields you will obtain, the distribution will be integrable. It will be involutive and it's integrable, but it is involutive and it's integrable because it's the lift of some distribution that is involutive in a certain fixed manifold.
Okay.
So, if you can go from the finite dimensional cases to the infinite one, in some case, it works. The Frobenius work. But if not, there are vector fields that do not come from the leaves of something that it is defined on finite dimensional jet manifold. Doesn't work.
Okay, thank you.
Yeah, thank you for your question.
So, more questions or comments? No? Okay, so thank you all for attending. Next week, we will have Oscar talking about Lie systems, right? So thank you all and see you next week.
Thank you. Xavi, do you have any a moment? Yes, to talk about
Yes, sure.
Right.